Thank you, François. It's great to be here. I had a very fun couple of days. The cafeteria is amazing. So I'm going to try and keep this short because I have 10 minutes less than I thought I did because there's 10 minutes of questions. So I'm going to skip the introduction. So the introduction wasn't going to say much that you don't know anyway. Integrable systems have ballistically propagating quasiparticles, and the ballistic quasiparticle picture explains a lot of phenomena like entanglement growth and whatnot. But on the other hand, in practice, when you think about transport in integrable systems, you often see anomalous stuff. So this talk is going to be about that anomalous stuff, and we're going to talk about it generally and also in this particular paradigmatic example where a lot of it was originally discovered, which is the XXZ spin chain. So that's the Hamiltonian. It's got three phases in the ground state. When delta is less than 1, it's a planar magnet. When delta is bigger than 1, it's an Ising-type magnet. The phase transition at delta equals 1, where it's the Heisenberg model. And so normally, if the model weren't integrable, you'd say that if you are at finite temperatures in one dimension, and in particular, if you're at high temperatures, none of this matters. You're just going to have diffusion no matter what. It's just going to be irregular hydrodynamics. But of course, the model is actually integrable, and so it's quasiparticles structure sort of coming up from the ground state remains stable at all energy densities, and therefore some vestige of the nature of the ground state transition survives in the high temperature spin dynamics. So in what used to be the easy plane magnet, now transport is ballistic, but the Drude weight that behaves in a very strange way with the anisotropy. I'm not going to talk about this today, but our work on this, our joint work on this is going to be talked about in Raman's talk on Friday. And so there's the easy axis regime where spin transport is diffusive, and there's of course this intermediate point you've heard a lot about where you have anomalous diffusion, sort of halfway between being diffusive and being ballistic. This only happens in spin transport. Energy transport, on the other hand, is always ballistic. Nothing interesting happens there. And so, okay, so all of this seems kind of bizarre. I mean, the fact that you have ballistic transport out here is reassuring, but here, you have no ballistic transport, even though you have ballistic quasiparticles, and here you have this weird anomalous exponent. So what's going on? And I should say there's a ton of numerical evidence for the main features in this phase diagram, especially the existence of a diffusive regime here and the existence of this anomalous exponent at delta equals 1. That's what this talk is going to be about. And it's going to proceed in 3 bits. In the first bit, I'm going to talk a little about how you get diffusion out of just thinking about ballistically propagating quasiparticles that scatter off each other. And that's going to, in some ways, echo some things that you've heard from in other talks in this workshop. Then I'm going to talk about an elementary solvable limit in which you can see various anomalous transport features showing up just because you have an infinite number of different types of quasiparticles. And finally, I'm going to talk about our theory with Raman of superdiffusion in the Heisenberg limit in terms of these simple kinetic pictures. So I mean, compared to previous versions of these stories you might have heard, this is going to be much more sort of pedestrian and boring. That I regard that as maybe a feature to some extent. Okay, so the starting point for all of this analysis is this idea due to Doyon, Yoshimura, and co. That says that the GHD equations look like the equations of motion for a classical soliton gas. You can think about it as a kind of hard rod gas, but generalized in the sense that each set of quantum numbers has its own hard rod radius with respect to each other. And so I'll say a bit more about that. And so the point is that when two solitons collide, they sort of jump back and forth. and the amount they jump by depends on the species they were. On the other hand, in the hard rod gas, this would just be independent of the rapidities, and that's why the general case is slightly more complicated in the hard rod gas. Okay, so why do we get fluctuations and diffusion from the hard rod picture? It turns out to be fairly straightforward, and what it has to do with is the fact that, okay, so first of all, where does dressing come from in the soliton gas picture? It comes from the fact that when you have a particle, a quasiparticle like the thick line here, that's propagating through an integrable system, it keeps getting bombarded by other quasiparticles, and whenever something else hits it, it jumps a bit, right? And so the average effect of these jumps is encoded in the dressing of the velocity and the fluctuations in the number of collisions that your test rod encounters in a given time gives you the sort of diffusive correction to ballistic propagation. So the important thing to note here is this factor of the velocity differences, because we were confused about this for a while. Now seems embarrassingly confused about it for a while, but we were. So the point is that if I have this guy moving out, down and to the right at some speed, other rods that are at almost the same speed don't really collide with it that often. They have to be moving, they have to start out really nearby in order to run into my test rod by time t. Whereas things that are moving in the opposite direction, you collide with a lot more of them in a given time interval, because pretty much everything that started out in this big window can reach you in that time interval. And so that's where this factor comes from. And it's going to be important in getting the diffusion constant right. Okay, so once you have this picture, you can convert it into equations, and so the basic point is that your quasiparticle, which has some basic group velocity, v, picks up position shifts that are proportional to the number of things it encounters, and so you can see that right. So this depends on how sensitive the velocity is to the number of quasiparticles the other species, and what the fluctuations of the other quasiparticle species are. And so, as I said in the previous slide, a really important thing is you need to figure out what range to average these fluctuations over, and that's given by this distance. That's the velocity difference times t, which measures how many of these other quasiparticles you've encountered on, what the typical range of these other quasiparticles you've encountered on timescale t is. Right. And so once you have these two things together, you immediately see you're going to get diffusion out of this t squared times this 1 over t, and all that remains is to plug in these prefactors, which have to do with the static fluctuations of quasiparticles of particular species in a thermal ensemble in an integrable system, and that would have been a fair amount to work out, but fortunately we could just look at this paper by Fenley and Soler, and so when you put all of that stuff together, you end up with this formula for the variance of the position of a quasiparticle that initially started out at the origin once it's propagated out for a time t. Okay, and so once you have this, what you're going to see is that you can then, once you have this formula, you can then try and rework it into an expression for the actual diffusion constants of conserved quantities. And for this, it's helpful to go to the much more systematic form factor calculation that Jacopo and Ben and Denis Bernard did around the same time. slightly earlier, crucially. But morally what's going on here is that this is what each quasiparticle position fluctuates by, and each quasiparticle is carrying, let's say, a charge or a spin that's given by its dressed charge, and so it's clear that the actual fluctuation in the conserved quantity on top of its ballistic motion is going to be given by some squared effective charge times the variance of each of the individual quasiparticles. And so this probably can be derived from this formalism, but we haven't been able to do it. And in some ways, the recent paper by Jacopo and Marco Medeniak and co-workers kind of fills that gap. Okay, so the basic strategy that's behind all of the stuff we're doing is that in order to figure out what happens over some finite timescale t, you need to say, well, let's think about the effective fluctuations of the thermal ensemble on the length scale corresponding to that timescale t. So the static fluctuations in the initial state plus the fact that you scatter off these static fluctuations gives you a variance to the quasiparticle position, and that gives you diffusion once you convert it into a variance in the amount of charge that's been transported. Okay, so that's the basic story behind diffusion, and you've heard a lot more about it, so I'll switch gears now a little and talk about how you get anomalous stuff out of this framework. And to introduce the anomalous stuff, I'm going to go away from the GHD framework a bit, and I'm going to talk about a limit where all of this is really elementary, and you don't need any beta ansatz at all to do the calculations. And that limit is the easy axis limit of the XXZ spin chain. That's a limit where, to leading order, all that's happening is an Ising interaction between spins, and then you perturbatively add in the hopping, which is the XX plus YY part of the Hamiltonian. So to make my life even simpler to start with, I'm going to go to this slightly funny limit where the temperature is infinite, but I have a big chemical potential so that the actual number of upspins in my system is quite small. And because the temperature is high, I can just think about these upspins as sprinkled in some Poisson way around the system, and now I can think about how this guy moves. And so a few things are fairly obvious at the outset. So a single upspin can move at first order in perturbation theory in the hoppings because there's nothing stopping it from going around, from moving. A clump of 3 upspins can only move together at third order in perturbation theory because otherwise you'd change the energy of the system, and that'd have a denominator. And so if you look at the initial state, it has some exponentially small density of very large strings, and these very large strings are stable because the model is integrable. So that's why I need to invoke the fact that the model is integrable. So they don't disintegrate into smaller strings. Okay, so a good way to start trying to think about this is to say each n string is just some sort of free particle because the problem is so dilute. And you have a question? Yeah. This process is off resonance, so it can happen, but it doesn't. So yeah, I mean, the process where you sort of, I don't know, where you break, the thing that's forbidden is the process where you take this 1 and 3 and you reconstitute it as a 2 and 2. That's the thing that integrability doesn't allow you to do. Obviously, in order to move, the 3 has to become 1 and 2, that's off shell, and then you have to move the second one, then you've got to move the third one, then it comes back. But the point is that this object can't disintegrate. It can only move, it can only virtually disintegrate. It's got to come back. Is that point clear? Well, you have to I don't understand. So you have three, this is a third, so you've got to move this guy 1 over, and now you've got to move the next guy 1 over, and you've got to move the third guy 1 over. Yes. Yeah, but it's exact because the model is integrable. Yeah. That's the important thing. In a non-integrable system, what would happen is that you would still have the approximate conservation law, but the first thing that would go is that this 1 and 3 would reconstitute as the 2 and 2, which maintains the same number of domain walls, but has different particle content, right? That's not allowed because the model is integrable. Yes. In the limit where density is sufficiently low, these are stable asymptotic states. They can't go anywhere else. Yeah. And that's only because the model is integrable. The moment you break integrability, that goes out the window, and you go back to things you're more used to thinking about. Right. Okay. So the simplest thing you do is just think about each n string as a free particle, and it moves at nth order in perturbation theory, so it has a dispersion relation that you would naively guess to be just the standard free particle dispersion, but with a bandwidth that's exponentially suppressed in n. And you can now think about what this does in terms of spin transport. So each upspin carries spin 1 in this simple limit, and so in order to have a non-trivial contribution to the autocorrelation function from 0, 0 to xt, you need some string that started at 0 to have propagated out to the position x and t. And so you can do this slightly more carefully with Bessel functions, but basically what happens is that under ballistic propagation, each string spreads out in a time t over a distance that's the velocity times t. And it does so more or less uniformly, up to some oscillations we don't care about. And so the propagator is then going to be the density of things you could have had at the density of n strings you could have had at the original point, and how far they went by time t. And so density is exponentially down. It goes as f to the n. Delta, the velocity is down by 1 over delta to the n. And you put all this together, and you have the sum over factors that does what it does. So you see that this equation has two possible asymptotic behaviors. So in one case, f times delta is less than 1, and you don't care at all about the heavy strings. You can truncate your problem at the 1 strings and go home, and everything's nice and ballistic. On the other hand, when f times delta is bigger than 1, then what happens is that if you sit at some position x comma t, you're dominated by the heaviest string that's managed to make it out to that position. Anything else, anything heavier, you haven't gotten there. Anything that's lighter is subleading, and so you're dominated by the leading guy that made it out to that position at that time. And so, and that you can get by this very simple calculation. It's basically logarithmic in t over x. You plug that back into this equation, and what you find is that in this regime where f times delta is bigger than 1, at this level, the autocorrelation function goes as an anomalous power of t. And this anomalous power is continuously varying. It depends on the filling compared with the anisotropy parameter. So this seems nice. It looks anomalous, which is good news because that's what we're trying to get. On the other hand, diffusion doesn't look especially special, right? There's just some number between 1 and 0, and as you take delta to infinity, this number goes. This sort of correlation function apparently goes as t to the 0. So is that true? Well, in some sense, obviously not. And the reason it's not true at any finite density is that quasiparticles scatter off each other. And so you can get a pretty good sense of what the scattering process is by just thinking about sending in, okay, so black here is an upspin and white's a downspin. So my heavy quasiparticle is this guy. It's not really going anywhere ballistically on this timescale. But what happens is that when the light string comes and hits the heavy string, it can only make it out here. Right? At this point, it's run out of obvious things to do that are perturbatively allowed. But the thing it can do is it can transmit a downspin through this domain through this black domain. And this downspin can then emerge from the domain on the other side and continue to propagate as an upspin. So the upshot of this process is, well, the two things that happen. So the first thing is that, and the most important thing is that the heavy domain has now moved by 2 steps, right? And the second thing is that while the light string is going through the heavy string, it's flipped its sign. So it's effectively, it's gone from being a thing that carries an upspin to a thing that carries a downspin while it's in here. So those are the 2 basic phenomena that are in some sense beyond the free particle approximation. The first one tells you that, that these heavy objects are actually Brownian particles because as they're sitting there, they keep getting hit by the light magnons that go through, and each time such a collision happens, they sort of step 2 steps over in some random direction, and so over time this is going to make this guy diffuse, right? And that's going to be at short to intermediate times its leading behavior. And so once you include that diffusion process, what you find is that right here, right around the origin, where you would be dominated at some given time by really heavy strings that haven't gone anywhere. It's not true they haven't gone anywhere. In fact, they're just moving as Brownian particles. They haven't started moving ballistically yet. If you go to very, very late times, well, the triangle emerges from the parabola, and the end string starts going ballistically. And so what happens is that if you sit at some fixed time and work at small x, you see that when n is big enough that this inequality is satisfied, the string's just diffusive, and when n is smaller than that, the strings are ballistic. You figure out what this n is, it goes as log t. You can see that from the fact that Vn is delta to the minus n, basically. Okay, what's the contribution of correlation function? At short distances, it's basically the number of things that are still diffusing, and that goes as this expression. As you can see, now you get the somewhat sensible answer that as you take delta to be very large, your autocorrelation function behaves diffusively. It approaches diffusion, but any finite magnetization, you have some anomalous exponent in the return probability. Okay, and the second thing to note is that, as I said, things that out here on these rays that are far away from the diffusive parabola, motion is still primarily ballistic, but these guys that are moving out ballistically have gone through. So if you think of, okay, so now let's go to the limit where the magnetization is small rather than large, and just hand-wavily talk about what happens. So in this regime, a magnon spends only sort of order mu more time being an upspin than being a downspin. So the effective magnetization it carries, because it's almost completely screened, is just of order mu. And precisely at half filling, there is no effective magnetization, and what happens then is that these contributions, which go as mu squared, die out completely, and all you're left with is this broad central feature that was due to the Brownian diffusion of the heavy quasiparticles. Okay, that's a story. You can make it slightly sharper with generalized hydrodynamics, okay, so can everyone see there's a sort of like a tiny purple line moving out to the right here? I'm not sure if the video quality is high enough for that, but okay, so away from half filling, what you find is that you have this, in the gapped phase, what you find is you have this big diffusive blob, and in addition to this big diffusive blob, you have these small rays shooting out that are the light, mostly screened out quasiparticles that carry some residual ballistic transport, and eventually, as you go to half filling, all that stuff dies out, and all you have left is the big diffusive blob at the origin. Okay, so that's how the ballistic part of the motion vanishes in the half filling limit of the XXZ spin chain. All right. So now let's go away from the solvable limit, and let's try and use this insight to go back and think about what happens as you move towards the isotropic point. In order to do that, we're going to need a little bit of beta ansatz information that I'm just going to quote. It's from this tour de force paper by Jacopo, Ene, and co-workers. I have no idea where these formulas come from, except they come from the appendix of this paper. Anyway, ask Jacopo if you have questions, I suppose. Right, so we're going to implement this program of like saying, okay, so you're working at half filling, and your magnon moves out a certain distance, and you want to ask what the diffusion is. Well, one way to think about it is, again, you say, okay, your S string is moving out with a velocity vs. If you think about the variance of an initially localized bump of magnetization, it goes as Vs times d quantity squared times the dressed magnetization carried by the S string. Now, if you are being naive, you say this is just 0 because the S string is completely screened, right? But the crucial point to make is that when the S string is propagated a distance t, it hasn't really sampled the system well enough to know that it's at 0 magnetization. It still thinks it's a magnetization that's 1 over square root of the distance it's traveled. And so once you plug that in, once again you have a t squared, you have a 1 over t, and then you can plug in all this beta ansatz information, and when you do that with the prefactors, you get this closed form expression for the diffusion constant, and this closed form expression gives you a divergence of d as you approach the isotropic point, and the divergence goes as 1 over eta, where eta is cosh. Sorry, where the anisotropy is cosh of eta. So delta equals 1 means eta equals 0, and so this is 1 over delta minus 1 to the 1 half. I should say that this divergence was discovered, I guess it was first posted by Jacopo and Ben and co-workers the same week as we posted paper. Okay, so that's what happens with diffusion. Now let's move on and think about super diffusion. And so, and you've probably already heard a few versions of the story, but here's one more. So once again, this is what happens as you take. This is what happens to velocities and the occupations and so forth in the vicinity of half filling, in the vicinity of the isotropic point. What we're going to do is we're going to say, well, this looks. The isotropic point looks sort of like a critical point at which your diffusion constant diverges, and you're going to have to cut off the divergence in some self-consistent way. And the natural way to try and set that up is to write down a scaling ansatz for the anomalous part of the spin response, and that's the response near the origin, and so that's going to. This is a fairly general scaling form with undetermined exponents. Now, the first thing to note is that from all the stuff that I've told you so far, it's clear the crossover length scale between knowing you're at half filling at the isotropic point and not knowing where you are is set by whether you've traveled long enough distance to resolve where the magnetization is 0 or non-zero. And that immediately gives you that mu is 1 over the square root of the correlation length, and that gives you that fixes this exponent at 2. Fine. Now you can ask, how long does it take to move spin across a distance, across a length scale c, in order to figure out what the dynamical exponent is? And to do that, you need to, I guess, go back to the original formula in the previous slide and notice that you're dominated. Okay, so you can cut this off with mu instead of eta, and you'll get 1 over mu here. You're dominated by the biggest string that's made that exists at magnetization mu, and that biggest string has an index that goes as 1 over mu. Any string that's much lighter than that doesn't contribute because it's screened. Any string that's much heavier than that doesn't contribute because its density is exponentially suppressed. And so the strings that dominate are the strings that have that have string index 1 over mu, and these guys have velocity by this expression that goes as mu. And when you plug that in, you realize that the time it takes to move across the correlation length is well, it's the distance over velocity. The velocity is going to be the velocity is mu. The distance is 1 over mu squared. And so what you get immediately out of this is that the time goes as 1 over mu cubed, and this gives you that the exponent z is 3 heads. So this is, if you like, as far as you know, the simplest argument from the quasi-particle picture for why you get the exponent 3 heads. So that's that exponent. What we don't know from this argument is, of course, what the scaling function is. And so at this point, we now have a nice argument due to Weir, in addition to a bunch of numerical evidence that this scaling form is not actually, that the scaling form is certainly non-Gaussian and probably is of the KPZ universality class. All right. So that's basically most of what I wanted to talk about. So once again, the two big things are that if you're away from half-filling, what you find is that, in fact, in some sense, spin transport is ballistic, but it's ballistic with an increasingly small ballistic component that vanishes as magnetization squared as the spin goes to half. And you have this big blobby leftover diffusive peak. That's the only thing you've got left in the limit of half filling. And so this thing that's left over is, you can think about it as, it's diffusive away from the isotropic point, and it's KPZ at the isotropic point, and where it comes from is this idea of quasiparticles propagating through a fluctuating and sort of screening medium. And so I guess this open question is a bit less open now, but there's still some aspects of it that are open. We don't really know how to fix the parameters in the KPZ equation, for instance. That's an interesting open direction. All right, so now I just want to summarize what I've said so far, and I'm actually going to finish in time, which is amazing. I guess that's what happens when you cut off about a third of your talk. So we talked about where the diffusive corrections to ballistic motion come from, and so the basic point is that they have to do with the quasi-particles are moving ballistically, but in a given time t, they scatter off the things that are in a window of size t, and those quantities are fluctuating with some fluctuations that go as 1 over square root of t, and that's where you get diffusion from. That's a very different way, but sort of equivalent, I believe, to the argument, the more general argument that Ben gave yesterday. And so these features diverge when you have infinitely many quasi-particles. Anomalous stuff of one kind or another is probably generic in that limit. And so the thing that's not generic is the vanishing of the ballistic piece altogether. But that happens because of screening at this half-filling point. Then the only thing you have left is either the diffusive piece or the anomalous piece. And so putting that, so I illustrated that in the XXZ spin chain. First, I talked about what happens away from half-filling, where you see this anomalous behavior in the local autocorrelation function. Next, I talked about superdiffusion at the isotropic point, and so the thing I didn't talk about today, but which you'll hear if you're still around on Friday, is what happens on the gapless side, and that's work in collaboration with Raman and some others, and you'll hear about it in his talk on Friday. All right, so thank you very much for your time. That's efficient.
Oh, yeah. So can you summarize what's the origin of the anomalous exponent? delta bigger than 1. I mean, is there some generic principle or?
Yeah, I think so. The generic principle is basically when you have an infinite quasi-particle hierarchy, you have you basically are summing up an infinite number of contributions to some transport coefficient, and when that sum is under very general conditions likely to diverge in one way or another, and when that sum diverges, you're going to have something anomalous happen, and this is going to be, I think, completely generic. The thing that's more unusual is the vanishing of the ballistic piece. But if you look at sort of at the full structure factor, it's going to have some weird exponent, like pretty much always, if you have infinitely many quasi-particle types, I think. Probably not, because of what François and Wojciech were saying, like at this point in my talk, which is basically that if you have something like this, some quasi-particle hierarchy, the really heavy quasi-particles are going to disintegrate before they have the ability to affect transport in an asymptotic way. And so they're just going to disintegrate, and you're going to get some diffusion that's set by the time scale in which these quasi-particles become unstable. And that could be a very long time scale if the system is nearly integrable. But the only circumstance in which I see it being more generic is if somehow very heavy strings are somehow abnormally stable against integrability breaking perturbations.
So is entanglement growth also sensitive to some of this physics, or is it just dominated by some sort of fastest modes?
Entanglement growth is mostly dominated by the fastest movers, but if you think about mutual information growth, that's going to be dominated by these slow strings. Right, so in entanglement, there's probably some kind of subleading thing that happens in late times, not very visible, but in mutual information, they're the main effect. Because what happens, you take mutual information between two regions, you sort of, you send off bell pairs from between them, they sort of go hit the two regions at a speed set by the velocity, and then they then fly off and there's no mutual information left. So it's only the guys that are very heavy and just got there that dominate the mutual information. So that's going to have all these anomalous exponents in it. Not the three halves, but all the others.
Yeah.
So this picture you have in terms of these quasi-particles that are sort of there's blocks of some things. So these are directly related to the bound state solutions of in Bethe-Ansatz. I mean, they are.
Yeah, that's right. At low density, those are the bound state solutions.
So are there? So what is the classical analog of such?
They do exist. I mean, I think you should ask Manas about that sometime. So if you in the Faddeev-Takahiro model, I believe there's sort of very similar looking objects in appropriate deformations that model. So still, I don't know, domain wall-like objects somehow. Yeah.
So I'm just trying to understand what you call diffusive correction. So if I take a sample here and measure spin conductance, yeah, will it be satisfied as a function of system size? Will it go like ballistic one or like Ohm's law?
So in the gapped phase at delta equals one, at delta greater than 1, it'll obey Ohm's law. But in general, when there is a ballistic contribution and diffusion as a correction, then diffusion is unimportant for this question. It's just going to be Landauer.
So in this regime where you call diffusive, it will be actually scaling,
yeah,
it will be
exactly.
just a constant, L independent.
Yeah, exactly. So in the regime I call diffusive, that's the XXZ model. In the gapped phase at half filling, you will get Ohm's law back. But in general, all that's happening here is a subleading correction to a ballistic piece.
So everywhere you only discuss subleading corrections to diffusive. Is it correct? Or?
No. So let me be clear about this. So
what is the conductance scaling? So you have three regimes, so two
yes.
phases and the critical point between them. So can you say what is a spin conductance scaling in all three regimes?
Okay, so spin conductance scaling if you're away from half filling, so there is a ballistic piece, it's going to go as Landauer with the appropriate, with the appropriate carrier density.
I'm not sure what you call Landauer. Landauer is formula which valid in any regime, yes. So what do you call
sorry, I just mean ballistic.
Ballistic.
So it's going to
independent.
It's going to be
length independent. Yeah. Okay.
There's going to be a length independent piece. There's going to be a correction. that goes as 1 over L.
Okay.
As you go to half filling, the prefactor of the constant piece is going to go to 0 as filling squared, and everything that's left over is going to be in the 1 over L piece. Okay? So, and in the super diffusive regime, you're going to get, like, I don't know, some anomalous exponent instead of diffusion. So it's what you think it is. It's not, there's nothing fancy going on here.
Okay. Further question? Okay. So thank you very much, Sarang. Yeah.